Thank you, Shah, for this great talk. Unfortunately, we are running out of time, but do not hesitate to ask further questions at lunchtime and let him eat at the same time. Next talk will be realistic neural networks with guarantees. It's provided by Mark Müller. So Mark, you're a PhD student, but quite prolific with a spotlight talk at ICML. Student at the SRI Lab, so ETH Zurich with Professor Martin Vechev. Sorry, I'm reading at the same time. Your research focus are provable guarantees for machine learning models for both certified and probabilistic certification methods, especially on neural networks. Thank you for being here today and eager to hear your talk.
Thank you very much for the kind introduction. As Melody just said, I'm Mark Müller from ETH Zurich, and today it is my pleasure to talk on robustness guarantees for realistic neural networks. And since it seems like there were some questions remaining over the specific internal workings of robustness verification that Shahab skipped over, maybe some of these questions will be clarified. And Shahab already provided a brilliant outline of what these methods can be used for, so I might skip over some of these slides or really go over them quickly. Let's get started by kind of outlining the problem. Over the last few years, we've seen deep learning-based systems really achieve remarkable performance on a wide range of tasks, in some metrics even exceeding human performance. And when we hear these headlines or say this, we mean that on the original data distribution that we used for training and then also used to collect some test set, these models perform better than human experts, or at least untrained humans. However, what we see in the real world is that, for example, here, if we do a street sign classification, we train our neural network on a data set of street signs, and it works very well if we evaluate it on a test set. But now, if we introduce some slight rotation, for example, that's chosen adversarially to be exactly, let's say, 3.71 degrees, then suddenly the network fails almost arbitrarily and leads to the classification to a turn left sign. Similarly, if we add some partial occlusion via tape or via graffiti or via random noise, as seen earlier, then we might even classify to a 120 kph sign. And while this is an academic curiosity, if you look at this in the lab, it can have fatal consequences if these systems are deployed in the real world in safety-critical conditions. And this leads us to the conclusion, which I'm sure all of us here will agree to since we're at this workshop, that kind of standard robust or standard performance is not enough for real-world applications of AI-based systems. So what we need is really certifiably trustworthy AI systems. And of course, we can discuss what does trustworthy here mean and how can we certify this. So let me formalize this at least a little bit. Here I'll talk about general guarantees, but mostly robustness guarantees of neural networks. And this means for a given neural network that we have trained in whatever way we desire, we have a so-called precondition over the network inputs, which describes a set of inputs that we care about. In Shahab's example, these were these explanation sets where some variables are freed, but this might also mean pictures with varying levels of brightness, contrast, rotation, some translation, some random noise. A lot of this can be encoded in these preconditions. And then for all images that satisfy these preconditions, we want a postcondition to be satisfied. This can be a correct classification in the classification setting, or a small maximum error in the regression setting, or really a variety of other things. Okay, how can we decide now such properties? How can we decide whether a given neural network for a given set of preconditions satisfies the postconditions with all outputs? And this is where neural network verifiers come into play. They can provide formal guarantees that for all these inputs, the postcondition holds or does not hold by finding a concrete counterexample. With this short motivation out of the way, I'll give a quick outline of my talk. I'll first talk about neural network verification methods which can provide or generate these proofs, before then discussing a little bit how can we actually train neural networks for which we can provide such guarantees. Because while these methods can be applied in general to any method, often if the method is not trained specifically to enable this verification, we will not obtain any meaningful robustness guarantees, and we will just find counterexamples for every property that we ask about. Okay, let me get right into it. So here we have like a broad overview of what robustness verification with abstract interpretation can look like. And on the very left-hand side, we see an example of a precondition. Here we have an image of digit 8 from the popular MNIST dataset, and now we say we want to reason over all inputs that are similar to this image with respect, in this case, to L infinity distance, so we can vary each individual pixel separately by some limited amount, often, for example, a value of 0.3, which is quite substantial. And now we over-approximate this precondition, we over-approximate the set of images described by the precondition using a convex shape, in this case simply a hyperbox. So we describe each dimension with an interval, and then this describes a hyperbox in the input space, the image space. Now we can propagate this input through the neural network. And what do I mean when I say propagate? I mean we compute reachable set over approximations after every layer until we've reached the output space. So we've computed a set for which we have a guarantee that for any input in this input set, the output will be included in this region, in this over approximation of the reachable set. And we can now compare this over approximation against our post condition. In the case of classification, this simply corresponds to checking whether or not all outputs in this over approximation lie on the right side of a few half spaces, but we can encode much more complex properties as well. Let's maybe look at a more concrete example to make this a bit easier graspable. Here we again have our image of the digit 8 and then all similar examples. And here we define the precondition as all perturbed samples x prime that are in an epsilon ball around our original sample. Our post condition is here that all these perturbed samples x prime get classified the same way as our original sample x, which in this case classifies to the class 8. And we can equivalently write this, as already shown by Melanie, as an optimization problem. We can look at the difference between the output logit corresponding to the correct class and all incorrect classes, and then compute the minimum over our perturbation set, or over our precondition set. And if this minimum is greater than 0, then we've proven that for all possible inputs, the network always prefers the correct class to all incorrect classes. However, as Shahaf has mentioned already, unfortunately, this problem is generally NP-complete to solve, so often we have to do with something slightly worse. We have to take a lower bound to this, and if for this lower bound we can still show that the property holds, we've still formally proven that the network is robust in our example. And this is actually an incredibly general formulation, as we can encode arbitrary linear specifications this way. And if we include some extra layers in our network to encode nonlinear specifications, we can encode ands or ors, or really a lot of logic in this kind of very simple formulation. Okay, so what is the challenge in this process? The challenge is, of course, to compute tight lower bounds efficiently. And while linear layers are really easy to handle, and I remind you that most neural network architectures are compositions of linear and nonlinear layers. The nonlinear layers are really tricky to handle precisely. So this is what I'll focus on in this talk, and what a lot of recent research has focused on as well. But before I go into the details, I want to do a broad classification of the neural network types that we might be interested in. And here I look at the regularization level for certifiability on the y-axis. So how much we regularize the neural network to make this certification process easy, and the size of the neural network on the x-axis. In the upper left-hand corner, we have small networks that are heavily regularized, so their performance will be very bad and no one cares about those. Then in the lower left-hand corner, we have kind of relatively small networks that can be encoded exactly or analyzed exactly with mixed integer linear programming or SMT solvers, and which can be quite interesting for example, control tasks where input dimensionalities are low, or potentially also tabular data. Then on the upper right-hand side, we have kind of the opposite extreme. We have quite large, very large networks, at least for certifiability. So here we're talking about millions to tens of millions of neurons, but those need to be quite heavily regularized for these methods to apply. And this regularization comes at the price of accuracy. So what we really want to go for is what I have deemed interesting or realistic or challenging neural networks, which are of moderate size that is still sufficient to solve some perception tasks at least, that are here on the lower right-hand corner, but are also only weakly regularized so that they still obtain good performance on both the robust and standard task. Okay, so to give a brief recap, we are mostly talking about ReLU networks here, and here I've illustrated the ReLU function, the rectified linear unit, and we assume that we have pre-computed bounds Lx and Ux on the input of this ReLU. And now if you want to compute the convex relaxation, given these input bounds, we obtain this as this convex hull shown here in blue. Now what we can do to handle all the nonlinearities in our network is we can apply this so-called triangle relaxation to every single ReLU in our whole neural network, and then just compute the polyhedron over approximation of our output space. If we do this, we obtain the so-called single neuron convex relaxation barrier that's illustrated here. And while this is quite moderately efficient to compute, it's not super precise. So to tackle these challenging neural networks that I talked about earlier, this is not enough. So one way to tackle this is to use so-called multi-neuron relaxations. Conceptually, if we can approximate all neurons in the whole neural network jointly and simply compute the convex over approximation of the exact convex over approximation of the neural network's outputs, this is sufficient for exact robustness verification. So that would be great. So let's look at this in a bit more detail. Here on this face of the prism, you will recognize our triangle. And you can see that we just extrude it in the x1 direction. And this is because here we look at two ReLUs with inputs x1 and x2 and outputs y1 and y2. And since we cannot leverage any interdependence, any relation between those two neurons because we treat them separately, we effectively get this very large or high dimension or large volume output approximation. If we can instead leverage all the relational information that we have on the inputs x1 and x2 and approximate the output set jointly, then we get this much tighter, much smaller volume over approximation of these two layers. I'll provide a bit more detail on this now, and maybe things will become a tiny bit clearer. So how can we compute this? So we first realized that here for our two neuron example, and also generally, ReLU layers are piecewise linear. That means if we split our input space into the piecewise linear regions, it really becomes trivial to approximate simply with linear bounds. Let's look here at our diamond-shaped input region, and we observe that on each of the quadrants, we can replace the layer with a linear function. So let's do that. Let's split our input region into these quadrants. And now in each of these quadrants, we can compute exact bounds on the output of this individual ReLU layer. If we now take the convex hull of all of these input-output regions, this is the tightest possible convex relaxation of this set of ReLUs. So far, so good. Unfortunately, computing this convex hull is also exponential in the dimensionality, also the number of neurons. So this is not great. So doing this for the whole layer is unfortunately intractable. But what we can do is we can use approximate convex hull computations instead of exact ones. And in fact, we need to ensure that this is sound over approximation. So we need an over approximate convex hull computation. And as you see here, we have kind of 4 input-output regions in red. And if we have a method that can only take 2 input regions at a time and compute their convex hull, you will see that there are a large number of possible orderings to do these convex hull operations. And what we show is if we do a clever ordering, we can actually save a lot of complexity in this problem. So we do this, and here we show the comparison of a single neuron abstraction in green, our approximation in orange, and then the exact version in blue. And precision is normal, or this shows the normalized volume, so precision increases towards the bottom. And what you can see is, while a single neuron relaxation, in this case, has factor 5 higher volume than doing the exact convex hull, our approximation has only a 5% increase, and at the same time, it's 200 times faster. So this is already good. Unfortunately, this is still not enough to compute convex relaxations of all neurons in a layer jointly. So instead, what we do is we realize that, in fact, many neurons have only weak interactions. So there, it's not very important to capture their relation information. So we group our layer into many small overlapping groups, and for each of them compute these multi-neuron relaxations. And this gives us a performance that is close to computing relaxations of the whole layer jointly, but much more computationally efficient. So this is one approach to obtain tighter lower bounds. Let's now look at the separate orthogonal approach, and that is called the branch and bound procedure. So the high-level idea is, instead of computing a convex over approximation of our value for this whole input interval from the lower bound to the upper bound, we simply introduce a case distinction where we first treat only inputs that are below 0 and then only treat inputs that are above 0. And due to the piecewise linear nature of the ReLU layer, or the ReLU activation, on both of these splits, the ReLU becomes linear, and we can again treat it exactly, capture it exactly, just as any linear function. So how can we do this computationally? Recall that we can cast kind of robustness as an optimization problem. This is shown here again, where we have the output of the neural networks h of x prime and with the index I and y and I. And now we can encode the neural network effectively as constraints, simply by replacing the linear layers with linear constraints and the nonlinear layers with corresponding nonlinear constraints. And unfortunately, this is a now highly non-convex optimization problem, difficult to solve. But what we can do is we can effectively replace all these nonlinear constraints with linear relaxations. And then we get a linear optimization problem, which is very easy to solve. So far, so good. Now we can add the branching constraints simply as an extra constraint in our optimization problem, where we say this input is supposed to be smaller or larger than 0, and we replace this one ReLU with a linear layer or with a linear connection. So far, so good. There are some technical challenges, and we can get this min-max optimization problem, which is easy to lower bound, but I won't get into these details. We have one more problem though. Unfortunately, if we do this with every single ReLU in the network, then we have to treat combinate or exponentially many combinations of splits. And while each of these linear optimization problems is quite easy to solve, solving exponentially many of those is still infeasibly hard or infeasibly slow. So what we do instead is we only introduce these case distinctions or these splits as needed in the following way. We start with the whole optimization problem where each ReLU is unsplit. And now we take this optimization problem from our queue of optimization problems. We try to compute the tightest lower bound we can. And then we see if this is sufficient to prove a property. If it is, great, we take it off the queue. If it's not sufficient, then we pick some ReLU using a heuristic that I won't discuss now, and split this optimization problem, introducing this case distinction, and through both new subproblems, again back onto the queue where this ReLU is split. Now we repeat this process over and over again, and then we have three scenarios. Either we run out of time. In principle, this is complete, but can take exponential time, so we use a timeout. And in this case, we cannot really say anything about the problem. It's unknown what happens. So this is the incompleteness that Melanie mentioned earlier. Second option is the queue is empty at some point before we time out. This means we have shown our property for the whole input region. That's great. Or we might find a counterexample, which I've glossed over here in this description. So far, so good. So we've identified these two kind of orthogonal state-of-the-art directions to obtaining more precise lower bounds for the neural network verification problem. And we observed that they're not only orthogonal, but actually complementary. While the multi-neuron constraints require kind of a high one-time upfront cost to compute these constraints, then integrating them into the optimization problem later is relatively cheap. Our branch and bound approach, where we introduce splits, we have exponential costs the more splits we do, as we have more and more subproblems that get generated by each split. So if you can improve the tightness of each individual problem by quite a bit using our multi-neuron constraints, and thus reduce the depth required to prove a property in the splitting by only a bit, we can save exponential cost with this kind of one-time investment. And this is actually exactly what we proposed with MNBAB, combining the multi-neuron constraints with this branch and bound procedure, and then follow-up work. GCP introduced slightly different constraints, but this has been shown to be incredibly efficient, and these two approaches have dominated last year's neural network verification competition. Technically, There are some challenges to solve, but on a high level, we can simply encode our multi-neuron relaxations as extra constraints when we simplify or linearize our optimization problem, and then we get some more Lagrange multipliers in our min-max problem, but this doesn't really matter so much. Technically, it's all the same. Okay, now that we've seen how we can verify neural networks once we've trained them, let's look at how can we train neural networks to become robust. And for this, let's look here at this illustration of a classification process, where on the left-hand side, we have the input space, we have an image of a husky again. Then in the center, we have a neural network classifier, and on the right-hand side, we have an output space where we look at the decision boundary between the broccoli and the husky class. And as we see, our image of a husky gets indeed classified correctly, so this is great. But unfortunately, if we add a little bit of noise, it suddenly gets classified as broccoli. If you look at this a bit more rigorously and analyze the whole epsilon neighborhood of our input, then we see that in fact there's a whole part, a whole region in the input space that gets misclassified. So this is not great. We want to train networks where this is not the case and where this is provably not the case. So let's have a look at how neural networks are trained. Kind of standard training simply propagates the original input. But as the original input gets classified correctly, it induces only a very small loss, here illustrated as this dashed blue arrow, and it does not really induce any incentive for the neural network to become more robust. So what we can do instead is so-called adversarial training. Here we've projected gradient descent, or PGD. And we first compute in every epoch an adversarial example, and then we train with these adversarial examples instead of the original samples. This is already quite good. This sample is misclassified, it induces a decent loss, it wants to make the network more robust, and indeed this significantly increases the empirical robustness, so it becomes a lot harder to find adversarial examples if we train this way. Unfortunately, we typically do not find the actual worst case adversarial example this way, which would be the point that's furthest from the decision boundary and sit in this upper left-hand corner. So typically these networks are not sufficiently regularized to actually prove their robustness. To tackle this, people have used the same bound propagation methods that we can use for certification to compute over approximations of the reachable set, and then we can compute the worst case error for this reachable set, here illustrated as this very thick blue arrow. This is exactly the differentiable verification methods that were mentioned earlier in the question. Unfortunately, all the methods that are fast enough to be used during training are quite imprecise, so we heavily over-regularize the network to become robust. And this comes at the cost of significantly decreased utility. So what we propose to do instead is we first compute an adversarial example to find some malicious or bad behaved region in the input space. And now we only propagate a small part of our original robustness specification. This allows us to compute much more precise, although not sound, approximations of the worst case loss. And if we train with them, we expect to get networks that are still quite robust, but much less heavily regularized and thus have higher standard utility. So let me quickly recap and compare. PGD training under-regularizes a network for certification. Standard certified training using sound bounds over-regularize the network, and hopefully our new method, Saber, is somewhere in between. And indeed, if we here look at a relatively small network where we can use mixed integer linear programming to compute the exact worst case loss, we illustrate the approximation error. And on the right-hand side of the vertical line of 0, we have over-approximations of the worst-case loss. If we find IBP, a sound-certified training method, always produce over-approximations. And the left-hand side, we have under-approximations, which we obtain with PGD. In contrast, Saber, our method, sometimes obtains over, sometimes under-approximation, and leads to a much smaller mean approximation error. And in fact, to look at how much smaller these errors are, or how much smaller our abstractions are, let's look at the growth of these abstractions as we propagate them through a single value layer. And here look at, maybe we can get rid of this. We look at the ratio of the output box size, here illustrated in gray, and the input box size illustrated in blue for a single value layer. And under some assumptions and with some math that I won't bore you with, we effectively get originally a linear growth with a small rate. Then we have a phase of strong superlinear growth before we go back to a linear growth region. And in fact, the region that we're interested in turns out to be the strong superlinear growth. And if we now look at the whole network instead of a single layer, we see that we in fact get exponential growth in the input box size. And what we show here is the difference of an IBP trained network, so soundly trained network that's heavily regularized in red, and a much less heavily regularized network in teal, where we have the loss on a logarithmic axis over the input box size. And what we see is the standard loss, so the horizontal line, is much, much smaller for the less heavily regularized network than for the IBP trained, more heavily regularized network. But the loss also grows much more quickly with the as we increase the input box size. Now we of course want to certify at the full input region, so let's look at how we can do that. Here we see the training box size, so how much smaller our training region is than the actual region, perturbation region that we care about. And here on the right hand side we have full IBP training, and on the left hand side we have very tiny boxes. And what we observe is, as we reduce the box size, we increase standard accuracy, we increase adversarial accuracy. And if we now use our precise MMBAP verification, then we can actually leverage this to also prove higher certifiable accuracies while still retaining the benefit of the increased standard and adversarial accuracies. In contrast, if you use kind of older, weaker verification methods, the regularization is simply insufficient to prove robustness, highlighting how important the recent progress in verification methods is, in fact, also for certified training. Let me show you some empirical results where the upper right-hand corner is best, illustrating certified and standard accuracy. And we show kind of this recent method Saber that tries to balance regularization as a teal diamond. And what we see is across all benchmark tasks that are typically considered in this field, Saber dominates all existing certified training methods, obtaining both higher standard accuracy and higher certified accuracy at the same time. Before I come to a conclusion, I want to briefly thank all my amazing co-authors who have made the work I presented here possible. And now to quickly summarize, we combine precise multi-neuron constraints with the branch and bound approach in a new type of verifier that combines these precise constraints with the branch and bound procedure, for example, MNBAB. And then this allows us to train networks with very small but carefully selected perturbation regions to obtain reduced regularization levels that yield to high standard accuracy, which, using these precise verification methods, can be still certified to yield high certified accuracies. With this, I want to thank you very much for your attention, and I'm happy to take any questions.
Thanks a lot for the great talk. Could you say a few more words on like exactly what objective you use to train using the box that you found somehow?
Of course, yes. So we use effectively a standard cross-entropy loss, but we plug in the worst case point in our reachable set into the standard cross-entropy loss.
Okay. So the worst case, not like some, well, you're not really actually pushing the whole rectangle somehow to be with the right, and you're using the worst case.
This is actually, it's equivalent. So I use the worst case over my box, and this is then equivalent to kind of pushing the whole box through the loss, and then kind of taking the worst case over the push-through box. So, but in the end, we take the worst case.
Okay, thank you very much.
Thank you very much, Mark. Just a question on the size of the models that you are able to tackle with these methods. Can you give us an idea where you are now, and what are your targets for the next years?
Good question. Yeah. So these methods have tackle network sizes of a few 100,000 neurons, a few million parameters. And in fact, actually in some recent work, we've scaled the width of these networks by a factor 16. So I'm not 100% sure how many parameters this gives us, but growth should be quadratic. The number of neurons should be linear. So like a few million neurons, some tens of millions parameters. This works still well if we use the certified training method. and obtain state-of-the-art result, but the improvements are really small. And in this work, we also see that if we increase the depth of these networks, we actually don't improve performance. Because the regularization, that is the extra regularization that is needed to keep the growth of these approximations in check, kind of overcompensates any gains in expressivity that we get due to the extra layers.
Thanks.
No worries.